The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let us start. Welcome, everybody. So first, let me just say a few general things regarding the logistics of this class. So you should have these three handouts: one organization, one outline, and then one is the for PSAT 1. So let me just go over briefly this organization and the outline. So first, in this class, there's no textbooks. There are, however, there are many reviews in the available, but unfortunately, none of those reviews, none of the single review is suitable for the whole course. So I have listed some of the reviews at the end of this organization. So along the way, I will point out some specific references or some specific parts of certain reviews if they are directly relevant. And also for this class, there's no recitation. For advanced for advanced courses like this, the department does not assign TA, so we don't have recitation. So I have my own office hour, which is Monday, 3:30 to 4:30. It's just 1 hour before the lecture on Monday. So if you have questions or if you have, just feel free to come. So if you have some questions, other time, if this if this office hour is not good for you, I'm also happy to set up some other time to meet you, or you can stay after the class to ask questions, etc. So whichever way is more convenient to you. So today we have these. So from now on, everything will be just on the web. You should download the future PSAT, or if I put any lecture notes or materials, and you should find them on the web. And I assume you can all find out the website of the course, and it's also listed here in the organization page. In the organization page. So any questions so far? Good. And this class, there's no exam. And the grades are solely based on PSATs and the fellow projects. And the PSATs will be due every 2 weeks. So if you look at the calendar, then there are about like 5 PSATs. Then for the last 3 weeks, instead of say handing a PSAT, you're handing in a small paper, just whatever topics you would like to choose about this about the holographic duality. Just choose one topic, write say 8 to 10 page paper, either a review or some calculation you would like to do, etc. So 5 PSAT is 75%, and this final project will be 25%. 20%. That's pretty much mostly. That's pretty much the logistics regarding this class. Do you have any questions regarding the grading, regarding the project or PSAT, etc.? Good. So let me say a few words about this outline. So this outline is way too ambitious. It gives you yeah, it just serves to give you a rough contour what we will cover, but really don't take it too literally, because the first we are not going to cover all 7 chapters. That would be too much. So last time when I taught it, I covered only 3 chapters. And so hopefully this time I will do 4. Hopefully this time I will do 4. And I may also just deviate from some of the things here, depending on the pace or depend on people's interests, etc. So this is going to be flexible. If there are certain things you would really very much like to hear, you can also let me know. I can think about it. In particular, among the 5, 6, 7, and I can think about it, maybe discuss some of them. Yeah, also, another thing you should keep in mind is that in this class, this is a class which will touch on many different subjects, say gravity, a little bit string theory, and also quantum field theories, etc. So in such a class, it's almost impossible. I think it's just impossible to really derive everything in a self-contained way. And also, I think some of your background are also very different. So we are not, so the certain part may not appear self-contained to some of you. And so if there anything which is not familiar to you, if I just mention it, if I just quote it, if it's not familiar with you, and you make sure, don't hesitate to ask me either during the class or after the class, so that I can help you to make up on that, And also to keep in mind, like other advanced graduate classes, you actually mostly learn outside the class. Inside the class, it's mostly try to provide you some motivations, guidance, etc., and give you a rough contour, and your own reading outside the class actually should be the main route you learn things. So any questions? So during the class, please feel free to ask questions. Asking questions is a great thing, because if something you don't understand, there's a very good chance quite a few of your fellow students also don't understand. So if you ask a question, you are not only helping yourself, you're also helping other people. And you also help me, because then I will know certain aspect is not clear to you, then I will try to emphasize it or repeat it, etc. So please do ask questions. And also, if you have any feedback on the class, say whether it's too fast, too slow, or problems are too hard or too easy, the PSAT is too short for you, just not challenging enough, and just let me know. Just let me know. Then I will try to adjust. And again, this is very important. Because this will help us to improve the class. Any other questions? Or any questions? Okay. Then let us start our lecture. So first we look at the hints for the holographic duality. Okay, so we start by doing a multiple choice problem. Okay, so what is your answer? Good. So why is gravity?
We don't have a quantum theory of it. We don't have a good quantum theory of gravity.
Good, good. So we don't have a good quantum theory of gravity. Any other reason?
Except string theory. No.
Yeah, string theory is still not the, I would say not yet the final quantum theory of gravity. Yeah, so.
Non-renormalizable.
Yeah, this is the similar to that we don't have a full theory of gravity, non-realizable, yeah.
The gauge theory.
Good. Anything else? Or any other opinion? Say you should choose any other thing, any other interaction rather than gravity?
Strong is the strongest one. Strong is the strongest one.
That's right. You can also choose gravity because this is the weakest one. Yeah, so the gravity is the weakest one. Okay. So yeah. So I think you have said most of the things. And the gravity is very different from the others. And in some sense, all the others are understood. And so A to C are now understood to be described by gauge series. In the fixed space-time. So the fixed space-time, in fact, say mostly we use Minkowski. And for example, QED, for example, electromechanism is described by QED, and the QED just U1 gauge field, U1 gauge theory plus a Dirac fermion, Dirac theory. And similarly, like if you include the weak interaction, so there's something called electroweak. It's described by SU2 times U1 gauge theory. Described by SU2 times U1 gauge theory. And also the strong interaction, you know now is described by SU3 gauge theory. So for all those cases, the basic theoretical structure is understood. So the basic okay. In principle, we can formulate those series from first principle, just use path integral. Say plus Wilsonian RG, Wilsonian realization group, just based on principle, realization group, and then you can actually formulate all those theory in a non-perturbative way. So in a sense, then any calculation of series can be reduced to certain algorithm. Okay. Of course, this does not imply we actually know how to calculate many quantities here. It just say in principle they are calculable. It just we often don't have the technical tool to calculate them. For example, even in QCD, for example, even for strong interaction, we don't have the technical tool to calculate certain things, but they are in principle calculable, and we can write down the algorithm to calculate it. And but for gravity, this is different. So for gravity, it's very different. So for gravity, so now we understand that a classical gravity is just equal to space-time. Okay, it's just a series of space-time. So this is the content of the general relativity, the general quantumtivity. But at the quantum level, we really don't have a precise idea how to formulate the theory. So there are many questions still not understood. Many, say, conceptual questions still not understood. For example, a space-time should fluctuate. Okay. The space-time should fluctuate because of the quantum fluctuation, because in quantum anything fluctuates. And then the natural question is whether this is still the natural question is whether space-time is still continuous. Okay. So this still not understood, or you need to replace it by something discrete. And it's not even clear right now whether space-time will remain a fundamental notion when you go to quantum gravity. Okay? It could well be that space-time will be replaced by something else. And there are many other questions. Say, for example, quantum nature of black holes. Or what should be the beginning of the universe? Etc. So all these questions are not understood. Also, gravity is the weakest interaction. It is actually much, much weaker. So as we will see, it's much, much weaker than all the other interactions. And then also people have been speculating, maybe actually this feature may also be actually a fundamental feature underlying the special role of the gravity. So at least for many years, it seems like it seemed to people that these questions and the gravity questions, they're completely unrelated. They're completely unrelated. They're completely different subjects. And those are well understood, but somehow those will lead completely new ideas. So it came out a great surprise So came out the great surprise in 1997 by Medicina. That they actually are equivalent. So the proposal of the Medicina is that quantum gravity is actually equal to field series. On a fixed space-time. Okay. So on a fixed space-time just means that there's no gravity here on the right-hand side, because if there's gravity, then you cannot have a fixed space-time. Then space-time should be dynamical. And so this is the equivalence between quantum gravity and just our ordinary quantum field series, and this is ordinary quantum mechanics, and this is a very non-trivial quantum mechanics which we don't yet understand. Okay. And this equality should be really understood as the different descriptions of the same quantum systems. So these are the two sides are different descriptions of the same quantum system. So it just depends on how you want to see it. So one way you see it, you see a quantum gravity. Then from some other way you see it, you don't see gravity at all. You just see ordinary quantum mechanics. Okay. And so this is the what this equality is supposed to mean. So this equality essentially, so let me call this equation 1, which I will often use later. So this equation 1 is really a unification which unifies quantum gravity with other field theory in a rather unconventional way, not in the standard sense of unification, but does bring them together. Okay. So now let me make some philosophical remark. So last time I have checked when preparing this class, this Medicina's original paper has been cited more than 10,000 times in the Slack database. And so there's a huge amount of work has been devoted to understanding this relation. But in my opinion, this subject is still in its infancy. And with many elementary, as we will see in the class, in the course, as course goes on, there's still many elementary issues which are not understood. And to us, this relation is still like a magic. And we don't really have a very good idea where this relation comes from. We have some rough idea, but not very precise idea. So the purpose of physics, of course, is to turn what looks like magic or art into some rules, so that become something trivial. So at the beginning, of course, the gravity, Newtonian gravity was magic, but in the end, and what Newton did is to make the gravity to be not different from the force we see in ordinary life. And similarly for other interactions we have seen before. Anyway, so So personally, I believe when we really fully understand this relation, and this really be a huge landmark in the physics, and comparable, say, to maybe to Newton's understanding of gravity, or Maxwell, or Boltzmann, etc. So the goal of this course is to help you understand at least how we our current understanding of this relation, and also to help you to derive the relate. So these are two very different objects, and in order to set up an inequality, you also need to define a dictionary. For example, this is like Chinese, this is like English. So you need to define a dictionary between the two, and what one says to the other. So we will also work out the dictionary, and also we will develop the tools and how to use this relation, and also discuss many features of this relation and implications. Okay, so the purpose is to help you to really to bring to the forefront, say, of this very exciting subject. So any questions? Good? No questions? Okay. So now let's move to, so after this introduction, so let's talk about this. Okay. So if you look at this relation, so looking from the right-hand side, so you just have some kind of ordinary field theory or ordinary quantum mechanical system, which we, in principle, know very well conceptually, without any gravity at all. Somehow, if you view it in some different way, then the gravity and the space-time and the dynamical space-time should emerge out of this. Okay. So in some sense, this one implies that the quantum gravity, so let me just use the quantum gravity plus the dynamical space-time okay, dynamical space-time. So it's important, it's a dynamical space-time, can really emerge from a non-gravitational system. Okay. It can emerge from a non-gravitational system. So the idea of emergence of gravity from some other degrees of freedom is not a really new idea. So as back as in 1967, Sakharov, who was a Russian physicist, Sakharov is a very common name. A very common Russian name, but this is the most famous one. This is the most famous Sakharov who has invented the hydrogen bomb for the former Soviet Union, and he was also the guy who also later I think got the Nobel Peace Prize for some human rights stuff. But he was also a very excellent physicist, and including this idea of emergence of the gravity. So what he observed is that he found actually certain the condensed matter. He would study, say, some materials, etc. Then he found that certain condensed matter systems can actually have mathematical description, which looks like a metric connection, and etc. Can be interpreted. Yeah, just to say mathematically looks like the equation for the metric and the equation for the connection, etc. And then he was speculating maybe the general relativity can actually arise just from some kind of electron systems, just from the ordinary condensed matter systems, and as an effective description. And in fact, in the 1950s, even before the Sakharov had this explicit idea, people working in GR, in relativity, they already found many striking parallel between Einstein's equations and also associated many phenomena with hydrodynamics. And so we know that hydrodynamics is really just an effective description. And if you just look at the river, so in fact it's the discrete water molecules. But if you describe those motion of the water molecules at the macroscopic level, and then you find the hydrodynamics. But the hydrodynamics does not apply at the more fundamental level. So it's more like some kind of effective theory. So in the 1950s, people already found that there are many features of Einstein equation. It's reminiscent, I should say, just reminiscent of certain features of hydrodynamics. So there's already this suspicion that maybe the gravity of space-time is actually can emerge out of something else. Just like the hydrodynamics is not a fundamental theory, it actually emerges from molecules, dynamics of the molecules. Anyway, so from the field theory perspective, field theory perspective, it's also natural to ask whether, say, massless spin 2 particles can arise as bound states, say, of lower spin particles. Say like spin 1, like photons, which are spin 1. So photons or gluons in QCD, electrons or quarks, etc. Okay, just from the so these are the spin half objects. And if yes, so massless spin 2 particle, in some sense, so when you learn GR, you might have learned that the massless spin 2 particle may be considered as a hallmark from gravity, because of the basic propagation, the gravitational wave. So the basic propagation of the gravity is through the gravitational wave, and that's propagated as spin 2 particles. And if you quantize the theory, a propagation as the spin 2 object, and when you quantize the gravitational wave, then they become massless spin 2 particles. They become spin 2 particles. So in some sense, if your theory can allow the massless spin 2 particles as say if your theory contains the massless spin 2 particles, then it must contain gravity. Okay. So for example, even in strong interaction, even in strong interactions, which are, say, the theory describes gluons and quarks. And gluons and quarks, they can indeed form. So these are the gluons and the quarks. So for such theory, in a strong interaction, they are indeed spin 2 bound states. Okay. The gluons are spin 1, quarks and spin half, but you combine them together, you can make up the spin 2 bound state, even just in strong interactions. But of course, in nature, those spin 2 bound states, they're all massive. They're all massive, okay? And there are some very unstable massive particles. When you create them in immediate decay, so they cannot be gravity. For gravity, you need massless spin 2 particles. But if you look at this fact, you cannot have the feeling, say, maybe I take the QCD, maybe I tweak it a little bit. Maybe I can make those spin 2 massive particles into some massless spin 2 particles. Then I would have generated gravity from a QCD-like series. And then that will be a revolution. And then you will be immortal. And, but unfortunately, even though this was a very promising idea for many years, and this hope was actually completely dashed by a powerful theorem of the Weinberg and Witten. So there's a powerful theorem from Weinberg and Witten say this can never happen. So this is then they're not possible. So this is this is 1980. So the paper, if you can take, if you want, you can take a look at the paper. So this is volume 96 and page 59. So they proved two theorems in that paper. So let me just copy the theorem down. Copy the theorem down. So they say a theory that allows the construction of a Lorentz covariant and the conserved current, 4-vector current, say J mu cannot contain massless particles. Cannot contain massless particles of spin greater than half with non-violation. Value of Okay, so this is the first theorem. So the second theorem I think I should have enough space. So the second theorem said that a theory that allows a covariant, Lorentz covariant, and a conserved stress tensor. So let me just call it T mu mu, a stress tensor, cannot contain massless particles. Of spin J greater than 1. Okay? So, so the key, so let me just repeat the theorem a little bit. So the first theorem says if you have a Lorentz covariant and conserved current, and then in such a theory, there's no charged particles can have spin more than 1/2. Okay? So there's no charged particle can have spin more than 1/2. Of course, this cannot contain graviton. And the second theorem says if you have a conserved stress tensor, Lorentz covariant and conserved stress tensor, then this theory cannot contain any particles with spin greater than 1. Okay? So of course, this cannot also contain a graviton. Graviton will be a spin tube. So, this theorem, yes?
Is there anything like about RG flow of mass? Like, so this is renormalized mass. So okay.
No, this is final mass. Yeah, just the non-perturbative mass. Yeah, you don't talk about even normalization here. Just this is the this is just a this is non-perturbative statement. Yeah. So this theorem turns out to be actually very easy to prove, and in some sense is rather instructive. And just to give you the sense of the power of this theorem, we will prove it in a little bit. And so before proving it, I will first make some remarks to make you appreciate the what these two theorems means. So do you have any questions before I do that? Okay, good. So let me just make some remarks on this theorem. So the first remark is that the theorems really apply to any particles, to both. So normally we say the fundamental particle is the particle which you put in your theory. Is the particle which say, let me say, call it rather fundamental. Let me call it elementary. So the particle which already appear in your Lagrangian, okay, and composite particles. Composite particles, say, would be some kind of bound state, or some particles which don't appear in your original Lagrangian. So this theorem does not distinguish them. It just as far as you have some particles, no matter the origin. So now let's try to see whether this theorem is compatible to the various things we already know. Okay, so let's first try to apply it to, say, QED. So the theorem is compatible with QED. Okay. So we know that QED is a U1 is a Maxwell theory plus the Dirac theory. Okay. And then the Dirac and the fermions in the Dirac theory interact with the photons in the Maxwell theory. So this theory have a massless photon of spin 1. And this theory have a conserved charge because say electrons, they do have charge. This theory has a conserved current. Has a conserved current. But this theory does allow a spin 1 particle. Okay, does allow the spin 1 particle. And this is not contradictory with the theorem 1. So theorem 1 said if you have a Lorentz invariant and a conserved current, then you cannot have massless particle of spin half with non-vanishing charge. Okay? So in the photon, in this case, photon is massless, but photon does not carry charge. Okay, photon is neutral under the electric charge, and so the existence of the photon is compatible with that theorem. Okay. And now let's look at the Lax theory, which also contains massless spin 1 particle. And the Lax theory, which contains the spin 1 particle, is the Yang-Mills theory. Okay. So Yang-Mills theory, for example, let's consider SU2 Yang-Mills theory. So the Yang-Mills theory have 3 gauge field, A mu A, and A is equal to 1, 2, 3, corresponding to the 3 generators of SU2 gauge symmetry. And from this 3 gauge field, you can combine them into the following form. Have A mu 3, then I have A mu plus minus equal to 1 over square root 2, A mu 1 plus minus A mu 2. Okay? So, 2. So you can easily check yourself that this A mu plus minus is massless spin 1 particle particles can create massless spin 1 particles charged under the U1 subgroup. Generated by sigma 3. Okay, so sigma 3 is the generator associated with A mu 3, and so those two are charged under this generator. So now naively we have a contradiction. because those are massless spin 1 particles charged under this. And the theorem 1 said if you have a conserved current, then you cannot have any particle with charged, any charged particle with spin greater than 1/2. Okay, but those are the spin 1 particles. But actually, they're consistent because, as you may remember, in Yang-Mills theory, there does not exist. There actually does not exist. The way out is that there does not exist a conserved Lorentz covariant current for this U1. For the U1 generated by this sigma 3 divided by 2. So this is actually compatible. So this is actually compatible because such a current does not exist. Okay? So you will show this fact yourself in your P-set. And, but you may remember if you have studied quantum field theory 2, then you may remember this fact from the discussion of long abelian gauge series. Okay? So in this course, we will, from time to time, use various facts of the, say, long abelian gauge series. But they are not essential. If you don't know long abelian gauge series, you can still understand this duality. You can still understand the relation 1. But of course, if you know gauge field, that will help you a lot. Okay? Any questions about this? Good. So let's continue. So this theorem does not forbid graviton from GR. Okay. So if you try to quantize the Einstein's general relativity around the flat space, for example, then you will find the massless spin 2 particle. So this is what we call graviton. And this is not contradictory with that theorem 2. It's because you may still remember when you learn the GR, you said in GR, in general relativity, there is not, there's no conserved. So here is conserved, not covariant converged, just conserved. Lorentz covariant stress tensor. Okay. So in GR, actually, there's no conserved and the Lorentz covariant stress tensor. So actually, the GR as a theory can admit graviton. But this theorem 2 is nevertheless very powerful. It's nevertheless very powerful. It says very powerful. It says all renormalizable yeah, just say none of realizable QFTs in Minkowski space-time, which is the one we normally work with, can have emergent gravity. Okay. So QCD-like series, no matter how you try to tweak the theory, the spin 2 massive bound state can never become massless. Okay, they can never become massless. Because those series, they do, for example, our QCD, our strong interaction, they do have a covariantly conserved stress tensor. Okay, a Lorentz covariant conserved stress tensor. But this theorem does not violate this equation 1 I just raised, because this theorem, even though it's very powerful, it does have a hidden assumption. Does have a hidden assumption. This assumption is so obvious and so self-evident that even though Weinberg and Witten, they're extremely careful people, they did not bother to mention it. And nobody, of course, in those times, nobody with the right mind would have mentioned such a thing. So the hidden assumption is that the kind of particles they are talking about, okay, is that the particles they are talking about, the particles which they try to rule out, live in the same space-time as the original theory. Okay. So if you write down, say, QED in Minkowski space-time, and then you ask about whether you can have some spin 2 particles coming out from QED, and then of course you ask about whether you can have particles come out from QED living in the same Minkowski space-time. Okay. And yeah, so in some sense this assumption is self-evident, but precisely this is an assumption which is taken advantage by this relation, which first envisioned by Martina, is that precisely in this relation, in this equation 1 which I raised, that the gravity actually does not live in the same space-time as the original theory, and does not live in the same space-time as the original theory. And so even in the early days, when people were trying to dream having such kind of spin 2 particles, they come from QCD-like series, there's already an immediate puzzle, because if you say take the gravity, say suppose the QCD-like series can have emergent graviton in the same space-time, then first your QCD series is defined in a fixed space-time. But now if it contains spin 2 particle, then the space-time itself will be dynamical. then where does the original QCD theory live on? Okay, and then you will just seemingly go into this kind of self-contradiction, like somehow how can that, yeah. Anyway, so in this relation, in the holographic duality, gravity does not live in the same space-time. Okay, so this in fact live in one dimension or higher, or they can be several dimensions higher, depending on the examples. So this avoids this theorem in an obvious way, and also avoid this conundrum I said earlier. Is that because they're in a different space-time, so the field theory is still in a fixed space-time, but then the gravity then can be dynamical. Then the space-time which gravity lives can be dynamical. Okay. So any questions regarding this so far? Yes?
So can you elaborate on what you mean by in GR there is no conserved Lorentz covariant stress tensor? Because the covariant derivative of the stress tensor
Right.
that vanished. So
no, covariant derivative is not conserved. This covariant conserved, not conserved. Conserved means the ordinary derivatives, not the covariant derivatives.
Got it.
Yeah. A covariant conserved stress tensor is not conserved. And if you write down a conserved stress tensor, then it's not covariant. Then it's not covariant. And yeah, right. Yeah, similar thing with this case for the gauge field. And in this case, gauge invariant current, gauge invariant and conserved current is not Lorentz covariant, and the Lorentz covariant gauge invariant current then is not conserved. Any other question?
Questions?
Yes.
Considering conformal field theory, every particle is massless. Could you construct a spin-2 particle which carries conserved energy momentum?
Sorry, say it again.
For conformal field theory,
Yes.
every particle is massless.
Yes.
And could you cook up a spin-2 particle which carries energy momentum, which is conserved and Lorentz covariant?
Yeah. For conformal field theory, indeed everything is massless. You can construct a Lorentz covariant conserved stress tensor. So that theory, from this theorem itself, does not allow a spin-2 excitations in the same space-time.
I mean, for conformal field theory, there's no spin-2 particle.
There's no massless spin-2 particle.
For example, in 1 + 1D, I can actually have arbitrary high spin particle just.
Yeah, but you don't have massless spin-2. You don't have massless spin-2 particles.
But all the particles in conformal field theory is massless.
No. It depends. Actually, talking about the massless in the conformal field theory is a little bit tricky. It's a little bit tricky, and they come in all kinds of spectrum. They come in the continuous spectrum. Yeah. But this theorem this theorem does apply to ordinary conformal field series. Yeah. So in those series you won't have massless. Yeah, when we prove the theorem, then you can see precisely what do we mean by massless spin-2 particles. Yeah.
What does it mean to live in different space-time?
If you stay in the course, then you will know. Yeah, we will see it later on. Yeah, but not for a while. Not for a couple of weeks. And maybe in a couple of weeks we will see it. Yeah, maybe in 2 weeks, 1 or 2 weeks. Any other questions? Okay, so now let me give you the proof, which is pretty simple, and use some elementary facts, very elementary facts. Because you see, this theorem contains very little input. Okay, those theorems really contain very, very little input. So if you can prove such a thing, it cannot be complicated. Or you cannot prove it. If you can prove it, it cannot be complicated. Because the input is so little, does not require any details, of a theory. So if you can prove such a theorem, it must be just from kinematics, not come from any dynamics. So indeed, that's how the theorem goes. So the proof, so we will do proof by contradiction, as you would naturally expect. So now let us suppose there exist, say, massless spin J particle, massless particles. So let's assume this series contains some series. There exist massless spin 2 particles, massless particles of spin J. Okay? And just from the Lorentz symmetry, you can immediately write down, so from what we learned in QFT 1, 2. So just by Lorentz symmetry, that it doesn't matter what is the nature of those states, because they must form a representations of the, say, Lorentz group and the Poincare group. So, and then you can immediately write down the one particle states of such particles. And you normally can write them as k and sigma. So k is just the ordinary space-time momentum. Okay. So for massless particle, of course, the k0 square should be equal to k square. Okay. And then the sigma is the helicity. Helicity is a projection of the angular momentum in the direction of your momentum. And for massless particle, and this for massless particle of spin J, this sigma can only be plus minus J. Okay, so this is helicity. Okay. So if you don't remember this, you can go back to review Weinberg's book. So the Weinberg's volume 1, QFT, volume 1, section 2.5 discuss how you write down the general one particle states for, say, in any quantum theory, as far as you have Lorentz symmetry. Okay. Okay. And the one properties of this sigma is that let's now consider rotation. Now let's consider rotation. So let's consider rotation operator. This is operation operator by angle sigma, by angle theta around the direction of the k. Around the direction of the k, which is the direction of the k here. Say. Okay. So let's consider the action of this on the state, on this one particle, this massless particle state. Then by definition, this just give you I sigma theta, k sigma. Okay. So this is essentially come from the definition of the helicity. And the k does not change. It's because this is the rotation along the direction of the k. Okay, so k itself does not change, but the but this is the eigenstate of this rotation by a phase. Okay. Again, you can, if you're not familiar, if you don't remember this, go back to the Weinberg's book. You can easily find it. So now, if you have a conserved current, so if you have a conserved current, if you have a covariant conserved current J mu, then you can always construct the charge, the conserved charge, which is the integral over J0. And similarly, if you have T mu mu, then from T mu mu you can construct a momentum operator, which is the T mu. Okay? So this is just the standard momentum operator in your field theory. So this is just still the setup. Okay? And of course, just by definition, the P mu acting on K sigma, you just get back K mu. Okay, because this is the momentum eigenstate. And if this is also charged, and if this particle is also charged under this conserved charge, then, so if charged under Q, under this conserved charge, then Q act on this state will also give you the charge Q. Okay, so this is operator. Maybe I should emphasize this is operator. These are all operator. And all operator, and then this should give you charge Q. Okay? So now we want to show that theorem, this two theorem implies, so with this setup, this theorem can, so we want to show two things. One, if Q is non-zero, that means if the particle is charged under some conserved charge, then J must be smaller than 1/2. Okay, cannot be greater than 1/2. And otherwise, so we assume there's a conserved stress tensor. Otherwise, J should be always smaller or equal to 1 at most. Okay? So that's what that theorem means, translated using this language. Okay? Any questions? So now let's prove it. Let me just do it here. So now let's prove it. I think we just have enough time maybe to prove it. So to prove it, let's just first list some elementary facts. First, just list some elementary facts. First, from the Lorentz invariance, for the Lorentz symmetry, we do have to assume Lorentz symmetry, okay? You can show, so this I will just write down the answer and leave yourself to show it, okay, in your P set. So if you look at the matrix element of this conserved current between two such states of different k, in the limit which k goes to k prime, you have Q k mu k0. Okay? And similarly, in this limit, get so this we'll do it in your P set, okay? So let me call this equation 2, this equation 3. So this is based on the following normalization. Based on the following normalization. Between these two, between the two states, okay? So this looks as a seemingly complicated. So this relation is actually very easy to see intuitively. So first, let me just you can prove it by let me give you just a quick hint. For example, regarding 2, is that you can first show that K sigma J0 sandwiched between the two, okay, when the K, in the limit when this K become the same, it's just given by Q divided by 2 pi cube, okay. So this is, again, somewhat intuitive, because K is an eigenstate of Q, because the K is an eigenstate of this Q hat, and Q hat is just the integral of J0. Okay, just integral of J0. And so you can imagine on the right-hand side there must be a Q, because these are essentially the eigenstate of the integration of J0. And then when you take into account all these delta functions here, and then the integral, and the relation between the integral, and then you will naturally find this the right-hand side is just Q divided by this. So once you know this, then you can immediately see the first line there, equation 2 there. Because first there's a J mu there, then the right-hand side must have an index mu. So the only thing can carry index mu is the K mu. There's nothing else. And also, you know, when the mu equal to 0, then you should just get the Q. Then downstairs you might have a K0 to cancel them. Okay? So this relation, in principle, you can just by intuition, you can just, by dimensional analysis or thing, you can just directly write it down. And similarly, in the second relation, the analog of Q, so Q is the charge associated with Q hat. The analog of the Q for the stress tensor is just the K mu. Okay? So you just relate, replace this by K mu. It just relates the Q by K mu. Then you get the second line. Okay? Yes, K by K mu, you get the second line. Okay, so but I will leave you yourself to prove this rigorously. So this is the second observation. It said for massless particles, which have K square equal to 0, and K prime square equal to 0, because these are unshell particles. So K square and K prime square should be equal to 0. And that means for any two particles, a massless momentum like this, you can see immediately, just by writing this down, this must be smaller than 0. Okay? So this should come from your high school physics. That K dot K prime should be smaller than 0. And that means that K plus K prime must be time-like. Okay? Must be time-like. Yeah, because this square is essentially given by this guy, because K square and K prime equal to 0. So this guy must be time-like. Okay? And so that means you can always choose a frame that the spatial part of this is 0. Okay? So you can choose a frame K plus K prime equal to 0. So such a frame is just k mu, say E 0. Say we put all this in the z direction, then in the 3 direction. Then you can choose k prime k mu equal to. Okay. Okay. This just follows that these two are two light-like particles. Okay, good. So now we can almost in business. Then there's still a third elementary observation we need to put here. So the third observation, which uses this formula. So let's now take sigma just to be j. Okay. Okay. So now, under a rotation of theta around 3 direction, okay, around this direction, which we have the momentum, so we choose a momentum to be in this direction, then you should have, so let me call that operator to be r theta. It's the rotation in the z direction, in the 3 direction. So this operates on k, j. So let's take sigma equal to j. Take sigma equal to j. So this should be just equal to expansion I j theta kj. And if this acting on k prime j, so k prime have opposite orientation as k, because this is minus e, okay? And the opposite orientation means your helicity should also change sign. So that means here it should be minus I j theta k prime j, okay? Yeah, because this is the rotation along the positive 3 direction. Okay, so now we are in business. So now finally we will try to, from those facts together, we will now see a contradiction. Now you consider this object. Consider kj, k prime j, say this r minus 1 theta acting on j mu r theta kj. So now let's consider this object. Okay? So this object I can evaluate it by 2 ways. First, I can just act r theta on those states. Okay? So r theta on this one just give me this. R minus 1 acting on that just give me opposite of this. Okay? So altogether, if I do that way, then I get the expansion 2 I j theta k prime j, j mu, kj. Okay? But I can also act this operator on this current. So this current should transform as a Lorentz vector. So if I do this way, then I should get just lambda mu nu k prime j, j nu, kj. Okay? So this acting on that should just effect a Lorentz transformation on j, and so this is a Lorentz transformation matrix. Okay? So lambda mu just the standard rotation matrix acting on the vector. So lambda mu just the standard rotation matrix, for example, just given by 1, 0, 0, 0. say cosine theta minus sine theta. So it's just a rotation along the 3 direction. Okay. So this is just the Lorentz rotation acting on the J. So now similarly, if you examine this quantity, similarly, if I just replace here by T mu mu, okay, by T mu mu, we are out of time, so let me be a little bit fast now. Similarly, if we replace that by T mu mu, then we will get the same thing, 2ij theta k prime j T mu mu kj, which obtained by acting R directed on kj. But when that R acting on T mu mu, then T mu mu transform as a 2 tensor. Then we should get lambda mu rho, mu lambda mu rho, k prime j, T lambda rho, kj. Okay? Right? So now here's the key. So do you already see the contradiction? So let's look at this equation. This is just like a vector. The whole thing is like a vector. The same vector. So this is like an eigenvalue equation. This sets, this lambda mu mu acting on this vector gets eigenvalue 2ij theta. So this is like an eigenvalue equation, okay? But if you look at this matrix, this can only have eigenvalue exponential plus minus I theta and 1, okay? So this is thing we are familiar with. So only have eigenvalue exponential minus I theta 1. So similarly with this equation, just you have 2 lambda, okay? So now that means if this quantity is non-zero, which we know it is non-zero from 2 and 3, it is non-zero, that this 2ij theta can only take value plus minus I theta and 1. So that means that j from here, let's say equation 4, and phi from equation 4, that j must be smaller than 1/2. Okay? Because there's a 2j there. Similarly, from equation 5, means j must be smaller than 1. Okay? So this is what we want to prove. Okay, so this is what we want to prove. Yes?
Aren't k and k prime tend to 0 in this reference frame? I mean, 2 and 3 is the limit k goes to k prime, and k plus k prime is 0, so...
Yeah, so I can take them, if j is greater than 1/2, for example, in this relation, if j is greater than 1/2, then the only possibility is for this to be 0. But we know when you take k go to k prime, at least in that limit, this is non-zero. And so this cannot be 0. So this quantity cannot be identically 0. Okay? Okay, so this gives you the proof. So if you find the loophole in this proof, other than they have to live in the same dimension, yeah, that would be great.
No, what if the whole matrix element is 0? What if the whole matrix element is 0?
No, the point is that the whole matrix element cannot be 0.
Yes, but this is
Because of this.
this is in the limit k goes to k prime, and there you assume that k plus k prime is 0. So it means both k and k prime should be 0, no?
Sorry? No, k plus k prime is not the, no, this is a spatial vector. No, this is a spatial vector. No, this is spatial vector. This is spatial vector. Okay, sorry, I'm a little bit late. That's all for today.